Hey, we're going to talk a little bit about domain, or at least domain and range. And I want to reiterate some things you should have learned in college algebra. But when we talk about domain, we're talking about real numbers. So we're talking about real number inputs and real number outputs. So real x's going in and real y's coming out. So in general, that means no complex numbers and nothing that doesn't really give us a value. All right. So domain is the inputs, which we can usually think of x, and the range is the outputs, which we usually think of as y. So if you're familiar with that, let's see if we can answer a few small questions here. We've got some graphs, which are usually easy to work with. The first one, it says state the domain and range. Well, the domain, remember, is the x values. So running from left to right, it looks like it starts at -3 and goes over to 1. And be careful what's included there. So -3 less than x, and then 1 is included, so less than or equal to 1. So the -3 is not included for the domain. We can also write that as a interval. Parentheses -3 to 1 bracket. And then if we do the range, we're talking about the y values that are used, and it looks like that is on the y-axis from -4 up to 0. Now in one place the 0 is an open hole, but in another one it's included, so we're definitely going to include it there. So we said from -4, which is included, up to 0, which is also included. So -4 less than or equal to x, less than or equal to 0. In a interval, that'd be bracket -4 to 0, close the bracket. Okay, should be fairly easy to read from a graph. The only problem you should have is if it's a graph that is a little hard to read or something happens that you're a little uncertain of. The other graph here, some type of rational function. It's got some arrows in places so it keeps going left and right, but across the x-axis it looks like it's defined everywhere but at 0, and that's kind of implied when you look at it, so it might be a little bit hard to tell if you're not familiar with it. Hate it when that happens. Let's see if I can clean that up. Pull back down a little bit. So for the domain, I would say every number but 0. So x does not equal 0, so that means it could be any other real number. That's the interval notation. So, that's the inequality notation. So if you wanted to write it as an interval, you could do it from -infinity to 0 open, union from 0 on to positive infinity. A little bit easier to work with the does not equal 0. Now the range looks like it picks up above 0. If you're familiar with the function, you'll know a little bit more about it, but the y's are greater than or equal to 0 here. And I see something I want to go back and change on the other one. Excuse me. Y's are greater than 0. So we can say that is from 0 open to infinity open. Let's go back to the first one we did, and in the range change this x to a y. That was just me being too excited, because the range is the y values. Okay, so if you got a graph, it's not too hard to tell which x's are used and which y's are used and relate that to domain and range. But what I want to talk about is implied domain now. So if you don't have a graph, you usually probably have some type of algebraic function, and in that case you kind of have to read it to determine what the domain is. Now when I talk about implied domain, there's a couple things that come to mind, and that would be where if you had an application problem and certain things don't make sense in the application. For instance, if we were talking about the height of your kid over years, we wouldn't have a negative time as far as a negative year. So even though the graph might look like a line, it definitely wouldn't go everywhere. Anytime we're talking about time, usually there's no negative. So even if it's something we can graph with a negative side as far as an equation, it may not make sense. So it's implied that we're not using just any old number. Other times that we have an understanding about the limitations of a function's domain are even roots. Remember that you can't take the square root of a negative number and it still be real. Square root of a negative number is complex. Okay, so we don't want negatives under roots. Denominators. Okay, remember if you divide by 0, that's undefined, so we can't divide by 0. And also logarithms cannot have a 0 or a negative in them. So we're looking for those three things. A even root cannot be negative. Okay, a denominator cannot be 0, and a logarithm can't be 0 or negative. It has to be a positive number. So if we're just given a function, we're going to look for those three things. And if none of those things apply, it'll be all real numbers. So let's kind of go down to our examples that we have here. So the first one here, we're going to state the domain. So A, f of x equals 4x plus 7. So in that case, we ask ourselves, is there a root? No, there's no root. Is there a denominator? No, no denominator. Is there a logarithm? No. So there's nothing that stops us from using any numbers, so the domain would be all real. And if you remember back, 4x plus 7 is similar to a y equals mx plus b, so it's just a straight line. The next one, B, y equals 7 times the square root of 4x minus 7. So let's ask ourselves those questions. Is there a root? And the answer is yes. So we can't have anything negative under that root. So we're going to take what's under that root and set it to be greater than or equal to 0. So we're going to set 4x minus 8 to be greater than or equal to 0, and we'll solve that to be x greater than or equal to 2. So that means we can only plug in the number 2 or larger if we want this thing to work. If we plugged in 0, 1, something negative, then it would give us an imaginary or complex thing, which we can't graph. Okay. C, f of x equals the fraction of 21x over x minus 7. So let's ask those questions. Is there a root? No. Is there a denominator? Yes. Okay. So we're going to take that denominator, and remember the problem with denominators is we can't divide by 0. So we're going to set that denominator not equal to 0. Okay. So x minus 7 not equal to 0. So when we get x by itself, we'll have x cannot be 7. So that means all real numbers except 7. If we plug 7 in, we get a nice number on top, but we get 0 on the bottom. Can't divide by 0. It's just broken. D, f of x equals 4 times 1.6 raised to the x. That's an exponential function, but let's ask the three questions. Is there a root? No. Is there a denominator? No. Is there a logarithm? No. So our domain is all real numbers, and you could try that. You could take your calculator and put any number you want up there for x, and it'll give you an answer back. Okay. E, y equals 4 times the natural log of 3x minus 9. Three questions. Is there a root? No. Is there a denominator? No. Is there a logarithm? Yes. Okay. So the thing inside the logarithm, the argument, cannot be 0 or negative. So we're going to take the thing inside there, 3x minus 9, and we're going to say 3x minus 9 is greater than 0. So comparing B and E here, in B you can take the square root of 0, it's just 0. So that's where we get the greater than or equal to 0. But with the logarithm, we can't take the log of 0 or a negative, so that's where we get just the greater than 0. So if I solve that, 3x is greater than 9, x is greater than 3. So I can use any number greater than 3. So if I put 3 in there, the calculator breaks. If I put 0 in there, the calculator breaks. If I put 3.1 in there, the calculator's okay. Okay. And the graph only exists in these regions that we are keeping. F of x equals 3x cubed plus 5x minus 6. Ask the three questions. Is there a root? No. Is there a denominator? No. Is there a log? No. So in that case, all real numbers. Okay. So it's important to know what numbers we can use in a function. It's also kind of important to know which numbers not to use in a function. So that'll help us out a good bit. All right. Thank you.